Welcome back to the Deep Dive, where we plunge into the latest research, extract the most important insights.
Help you get well informed without drowning in details.
Exactly. And today we're cracking open a really fascinating technical report. Muon is scalable for LLM training. Comes from the folks at Moonshot AI and UCLA.
Right. And if you're in the LLM training world, you know efficiency is it's the massive challenge.
It really is. And that's precisely what this deep dive is all about.
That's right. Muon, it's been around for a little bit, showed promise, definitely for smaller models.
Yeah, saw some good results there.
But the huge question, the sort of elephant in the room, was could it actually scale? These enormous models, billions of parameters, trillions of tokens. Could Muon handle that kind of load?
And that's where this paper gets super interesting, because it basically came back and said, yes. A resounding yes. So for anyone just tuning in, maybe wants the quick version for that short form edit, here's the core takeaway, like the 1-minute summary. Okay, get this. This paper shows how the Muon Optimizer, which works by kind of balancing how a model learns using matrix orthogonalization, can finally work for training huge AI models. They figured out two key things: adding in standard weight decay and carefully adjusting the update size for different parts of the model. So what's the upshot for you? Well, Muon gets roughly 2 times the computational efficiency compared to AdamW, the usual standard.
That means same performance, about half the training cost, measured in FLOPs. Huge.
Exactly. And based on this, they built Moonlight, a big mixture of expert model, trained on a massive 5.7 trillion tokens using Muon. It seriously pushes the performance boundary, better results with way less compute than older models.
And maybe the best part,
they open sourced it. The code, the model, the checkpoints, everything, so the whole community can jump in. Yeah. This really could change how we train LLMs, maybe even replace AdamW down the line. So yeah, if you're an AI researcher, ML engineer, or just really curious about how these giant models actually learn, stick around. We're going to unpack how they manage this, the clever tricks involved, and why this is such a potential game changer for LLM training efficiency. All right, so let's set the stage a bit more. We know LLM training is super compute intensive, right? Scaling laws dictate that bigger models, more data equals better performance, but also more cost.
A lot more cost. And yeah, Adam and AdamW have been the workhorses for years now. They're robust. They generally work.
But as models got bigger and bigger, what were the specific pain points with AdamW that made people start looking seriously at alternatives like Muon? Was just cost or something else?
It's mostly efficiency, yeah. AdamW is good, but maybe not the absolute most efficient way to find the best model weights in this incredibly complex high-dimensional space. As the scale just exploded, the search for more compute-efficient optimizers really heated up. And Muon, proposed back in 2024 by Kay Jordan and colleagues, offered this different approach.
Okay, you mentioned orthogonalized gradient momentum. Can we break that down a bit? What's the intuition? What does orthogonalized actually mean in this context?
Think of it like this. A model learns by adjusting its internal weights based on the gradients, right?
Yeah.
Sometimes the gradients might push very strongly in just a few directions, while other directions are almost ignored. This can be inefficient, maybe even unstable.
Okay.
Orthogonalization, using this technique called Newton-Schultz iteration, tries to keep the updates more balanced. It encourages the model to learn more evenly across all possible directions in its weight space. The update matrices are kept isomorphic, which is a fancy way of saying they maintain a balanced structure, preventing those few dominant directions from taking over.
Right, so it's like ensuring all dimensions of the learning space are explored more evenly, not just the loudest ones.
Exactly, promoting diversity in the updates. But the original work, while promising, kind of stalled at the scaling part.
Yeah, what were the specific hurdles? You mentioned size, distribution.
Precisely. 1, just raw scale.
Yeah.
Billions of parameters, trillions of tokens. Does the math even hold up? 2, distributed training. Muon's update mechanism is different from AdamW's. AdamW updates things element by element, which is easier to distribute. Muon needs to work with whole matrices, which is trickier across many machines.
Ah, okay. That sounds like a big engineering challenge.
It is. And 3, generalization. Would it work well for both the initial pre-training phase and the later supervised fine-tuning phase? Those were the big unknowns this paper tackled head-on.
Okay, let's get into the breakthrough then. 2 crucial techniques. The first one sounds almost too simple, adding standard weight decay. Why was that so important for making Muon scale?
It does sound basic, right? But it was absolutely critical. When they tried scaling Muon without weight decay, things went off the rails. The model weights themselves and also the layer output, RMS, basically a measure of the average size of the outputs from a layer. They just grew enormous.
It's like numerically unstable.
Exactly. They blew past the usable range of BF16, which is the standard numerical format used in a lot of LLM training because it's efficient.
Yeah.
When your numbers get too big for the format, you lose precision, things overflow, and the model's performance just tanks. It couldn't learn properly.
Wow. So adding weight decay, which essentially penalizes large weights, kept everything in check numerically.
Precisely. They just plugged the standard Adam W weight decay formula into the Muon update rule. Simple, but effective. And the results, like you see in their figure 2, were stark. Muon with weight decay clearly beat vanilla Muon, and importantly also beat Adam W in their tests, getting lower validation loss, especially in the long run, the overtrained regime.
Okay, technique 1, add weight decay. Got it. What was the second crucial piece? You mentioned something about inconsistent update scales.
Yeah, this one's a bit more subtle, but just as important. So Adam and Adam W, they have this nice property where the sort of average size of the weight updates stays roughly constant, empirically maybe around 0.2 to 0.4.
Okay, predictable updates.
Right. But Muon, because of how its orthogonalization works based on matrix shapes specifically, it scales with squirt1. Max AB, where A and B are the matrix dimensions, the update size naturally varied.
Depending on the shape of the parameter matrix it was updating.
Exactly. So if you had a big, wide matrix, like in a dense MLP layer, max AB is large, so the update size squirt1 max AB becomes tiny. Too small to learn effectively.
Okay, limiting learning.
But if you had a smaller matrix, maybe like the individual key value heads in grouped query attention max AB could be small, making the update size 1 max really large.
Leading to instability.
Potentially, yeah.
Yeah.
Jumping around too much.
Yeah.
So you had this inconsistency. Updates too small here, potentially too large there, not ideal for stable training.
Right, you need that consistency. So how do they fix that?
It was quite clever, actually. 2 steps. First, they directly counteracted that shape-dependent scaling. They multiply the update for each matrix by squirt max AB.
Canceling out the inverse effect.
Exactly. That normalized the theoretical update size across different shapes. But then they did something really practical. They noticed Adam W's empirical update RMS was around 0.2 to 0.4. So they added an extra scaling factor of 0.2 to the Muon update.
Why 0.2 specifically? Just to match Adam W?
Pretty much. By scaling Muon's updates to be roughly in the same ballpark as Adam W's, they could often reuse the exact same learning rates and weight decay values that people had already carefully tuned for Adam W.
Oh, that's brilliant. That saves a massive amount of hyperparameter tuning effort.
Huge time saver. And their experiments confirmed this worked. The adjusted LR method, using this 0.2 squirt max B scaling, performed better and showed much more consistent weight magnitudes across different layer types, as you see in Table 1.
Makes sense. And they also landed on using 5 Newton-Schultz steps and a momentum of 0.95.
Yeah, those seem to be good defaults, balancing performance and computational costs for the orthogonalization part.
Okay, so they figured out the math and the hyperparameters, but then comes the engineering, getting this to run efficiently across potentially thousands of GPUs. You mentioned Muon needs the full gradient matrix, unlike Adam W. How did they build distributed Muon to handle that without killing performance?
Right, that's where standard tricks like 0-1, which work great for Adam W, by just keeping pieces of the optimizer state on each GPU, don't quite cut it for Muon. Muon needs the whole gradient matrix for its orthogonalization step.
So more communication needed.
Potentially, yes. Their solution, distributed Muon, cleverly builds on 0-1. Think of it like this. Each GPU has its slice of the parameters and gradients. When it's time for the Muon update, they first efficiently gather all the necessary gradient slices from other GPUs to reconstruct the full gradient matrix locally.
Okay, so there's a gather step.
Then they perform the Newton-Schultz orthogonalization on that full matrix. Then, crucially, they only apply the part of the resulting update that corresponds to the parameter slice they actually own, and they can discard the rest. The full algorithm involves steps like reduce scatter first, then the gather, then the update calculation, then applying it locally.
It sounds complex, managing all that data movement. How did it compare to distributed Adam W in terms of efficiency?
Memory, communication.
Surprisingly well, actually. Memory-wise, Muon is better. It only needs to store 1 extra buffer for its momentum, whereas Adam W needs 2. Momentum and variance, so half the optimizer state memory.
Okay, that's a plus. What about communication? All that gathering sounds like it could add overhead. It does add a communication step, but they found ways to optimize it. For one, the Newton-Schultz iterations can run in BS16 precision, while Adam W often keeps its states in FP32. That alone cuts communication for that part by 50%. Overall, they calculated the communication workload to be in the range of 1 to 1.25 times that of AtomW. Comparable, maybe slightly more in some cases, but not drastically worse.
And the all-important latency. Did it slow down the actual training step time?
This is where it gets impressive. They found the extra computation and communication for Muon typically added only about 1% to 3% to the total time taken for the main, forward, and backward pass of the model.
Wow, that's almost negligible.
Yeah, and they used overlapping techniques, doing some communication while computation happens to hide even that latency. In their large-scale production training cluster, they reported basically no noticeable latency overhead from using distributed Muon compared to AtomW.
That's huge. So practical, scalable implementation achieved. Which brings us to the results. The big claim, 2x computational efficiency. How did they back that up?
Through scaling law experiments. They trained models of different sizes with both Muon and AtomW, carefully controlling for compute budget, FLOPs. And they plotted the performance, the loss, against the FLOPs used.
And Muon consistently reached the same loss level with fewer FLOPs.
Exactly. Looking at their Figure 1a and Table 3, Muon consistently required only about 52% of the training FLOPs to achieve the same performance level as AtomW under compute optimal training conditions. That's where the roughly 2x efficiency claim comes from.
2 times the efficiency. I mean, for these massive training runs costing millions, that's just staggering.
It really is. It changes the economics significantly. And to prove it wasn't just a theoretical scaling law thing, they actually trained a large model with Muon. That's Moonlight.
Right, the mixture of expert model. 3 billion active parameters, 16 billion total.
Yep, based on the DeepSeek V3 small architecture. And they fed it a massive 5.7 trillion tokens, all optimized with Muon.
How did Moonlight perform compared to other models, especially ones trained with AtomW?
Very competitively. They compared it at an intermediate checkpoint, 1.2 trillion tokens, Table 4, against their own AtomW trained baseline. Moonlight Muon significantly outperformed Moonlight AtomW across the board: English, code, math, Chinese tasks, especially strong gains in math and code.
Interesting. And at the full 5.7 trillion tokens.
At full training, Table 5, it held its own against state-of-the-art dense models trained on way more data, like Llama 3.3b trained on 9 trillion tokens, or Qwen 2.53b on 18 trillion. And it clearly beat models with similar architecture and token counts, like DeepSeek V2 Lite.
So it's not just efficient, it produces genuinely strong models.
Absolutely. And importantly, as shown in Figure 1b and Figure 8, it pushes the Pareto frontier. That means it represents a better trade-off between performance and the computational costs, FLOPs, required to achieve it. It's setting a new bar for efficiency.
Let's go a bit deeper into why Muon might be doing this. You mentioned the diverse directions intuition. Did they find evidence for that in the trained models?
They did. They used a technique called SVD Entropy, Singular Value Decomposition Entropy, to analyze the weight matrices. Basically, higher SVD entropy suggests the matrix is using its capacity more evenly, representing information across more dimensions rather than relying on just a few dominant singular values.
So a measure of that balance you talked about earlier.
Precisely. And they found, consistently across different types of weight matrices and different training checkpoints, Figure 4 plus Figures 9 and 10 in the appendix, that Muon trained models had higher SVD entropy than AtomW trained models.
So the empirical evidence supports the intuition.
It does. Interestingly, the difference was even more pronounced in the router weights of the mixture of expert model, the part that decides which expert network processes which input token. This suggests MODI models might particularly benefit from Muon's diversifying effect.
That makes sense. What about fine-tuning, supervised fine-tuning, or SFT? Did the Muon advantage carry over?
Yes and no. It's quite nuanced. If you pre-trained with Muon and fine-tuned with Muon, the resulting models perform best, Table 6. The benefits persisted.
Okay, consistency helps.
But here's the catch. They found an optimizer mismatch issue. If you took a model pre-trained with AtomW, which is, most existing models, and then tried to fine-tune it with Muon, you didn't really get much benefit compared to just sticking with AtomW for fine-tuning as well. Table 7.
Huh. So Muon doesn't magically improve an AtomW pre-trained model during SFT.
Doesn't seem like it, based on these results. It suggests that the benefits of Muon are really baked in during the pre-training phase. How the model fundamentally learns its core representations seems to be where Muon makes the biggest difference. Trying to switch optimizers later doesn't recapture that initial advantage.
That's a really important finding for practical application, right? It means you probably get the most bang for your buck by using Muon from the very start during pre-training.
Exactly. It's not just a drop-in replacement for AdamW during fine-tuning if you want the full efficiency gains reflected in the final model quality. The foundation matters. So, wrapping things up here, this report really makes a strong argument. Moonshot AI and UCLA have shown, quite convincingly I think, that Mewon can be scaled effectively for massive LLMs.
Yeah, those two key techniques, weight decay and the adjusted update scaling, seem to have cracked the code.
They really unlocked its potential, and the practical engineering for the distributed setting makes it viable.
Absolutely. That 2x efficiency improvement isn't just academic, it's potentially transformative given the costs involved. And open sourcing everything, that's fantastic for the whole field.
Totally agree. It lowers the barrier to entry, allows for replication, and lets others build on this immediately. It genuinely pushes the state-of-the-art in efficient AI training. But, like all good research, it also raises new questions.
Which brings us perfectly to our final thought for you, the listener, to chew on after this deep dive. Considering Mewon's effectiveness, especially the performance gains tied to its unique update mechanism and that curious optimizer mismatch between pre-training and fine-tuning, what does this tell us about what really matters in an optimizer? Are there fundamental properties, maybe related to these kinds of norm constraints or update diversity, that we should focus on more? How might digging deeper into these properties redefine our whole approach to training the next generation of AI models?
It's a fascinating question. There's clearly a lot more to understand about the dynamics of these massive optimization processes. Thank you for joining us on the Deep Dive.
We hope this discussion gave you some valuable insights into Mewon and the future of LLM training. Until next time, keep learning and keep exploring.